Mr. Anwoy Maitra. He is a PhD student at the Indian Institute of Science, Bangalore. And today he's going to talk on the continuous extension of complex geodesics. So over to you, Anwoy.
Okay. So first of all, I would like to thank the organizers for giving me the opportunity to speak at this conference. So today we will be talking about the continuous extension of complex geodesics. So in order to define that concept, we need the notion of Kobayashi pseudodistance. So let's get on to that. So it would be very useful to construct for every complex manifold X a distance kx such that holomorphic mappings are contractive with respect to this family of distances. A useful consequence of this, for example, would be that whole xy, the space of all holomorphic mappings from x to y, where x and y are two manifolds admitting such a distance, would be equicontinuous. In the 1960s, Kobayashi introduced a family of pseudodistances. They are not distances in general that satisfies the above properties. So how are these pseudodistances defined? So given a complex manifold X and points A and B in X, we define KXAB, the Kobayashi pseudodistance between A and B, to be infimum of the set of all summation from j equal to 1 to m rho d 0 zeta j, rho d is the Poincare distance, such that there exist holomorphic mappings f1 dot 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 fm from d to x such that a equals f1 of 0, fj of zeta j equals fj plus 1 of 0 for all j equal to 1 to m minus 1. This is the linking up condition, and fm of zeta m equals b. So what we are basically doing here is that we are taking a chain of analytic disks, chain because of the linking up condition, joining A to B, calculating the length of this chain using the holomorphically invariant object at our disposal, namely the Poincare distance, and then infimizing over the lengths of such chains to get the Kobayashi pseudodistance. So this is the same sort of thing we do in Riemannian geometry. So this is a natural definition. So we move on to isometries with respect to the Kobayashi distance. Whenever we study distance spaces, a natural object of study is isometries between them. So for complex manifolds X and Y, a natural object of study, provided Kx and Ky are distances, is the set of all maps from X to Y that are isometries with respect to the Kobayashi distance. Such isometries need not be holomorphic. A trivial example is the map Z goes to Z conjugate from D to D. Since D is the complex analog of the unit interval -1, 1, of particular importance are holomorphic isometries between D and a given complex manifold X. These are called complex geodesics of X. So it is elementary to show that Kx is a distance, true distance, in the domain Cn. Note, however, that we have not addressed the question of the existence of isometries. So turning to this question, Lempert proved the following famous theorem in 1981. If omega subset of Cn is a convex domain, then C omega equals K omega, where C omega denotes the Carathéodory pseudodistance on omega. The Carathéodory pseudodistance is a standard object. I won't define it. Its definition is similar to what we saw in the previous talk. But the importance of this theorem is that it implies that in an arbitrary bounded convex domain, there exist complex geodesics passing through every pair of points. In order to prove this, one uses a standard argument involving tautness because bounded domains are involved. So it's not very difficult, so I won't deal with that. That is a standard theorem. So, however, in many potential applications, existence is not enough. One needs information on boundary regularity. Turning to this question, Lempert proved the following. Lempert 1984. If omega subset of Cn is a strongly convex domain with Ck smooth boundary where k is greater or equal to 2, then every complex geodesic phi from D to omega extends in a Ck assumptions are strong convexity and Ck smooth boundary where k is greater or equal to 2. Then we get extension. So in view of this, it is natural to ask what weaker conditions on omega will guarantee the continuous, if not smooth, extension of complex geodesics to del D. Some conditions are needed, as the following example shows. So example, it is easy to show that a holomorphic mapping F equal to F1, F2 from D to D2 into the bidisk is a complex geodesic if and only if at least one of F1 and F2 is a holomorphic automorphism of D. Choose a holomorphic function g from D to D that does not extend continuously to del D. Infinite Blaschke products are examples of such functions. Then f, defined to be z going to z comma gz from D to D2, is clearly a complex geodesic because one is just the identity. Complex geodesic that does not extend continuously to del D. So some conditions are needed. So we turn to some recent results on boundary regularity. There have been a couple of recent results on the boundary regularity of complex geodesics. A result by Bharali, 2016, states that in a bounded convex domain with C1 smooth boundary that is supported from the outside by a certain kind of surface, ensuring, for example, that there are no points Xi in del omega at which del omega contains line segments starting at Xi in certain directions, every complex geodesic of omega extends continuously to del D. So I will just give an illustration to show what this supported from the outside means. So just bear with me for a minute. So this is roughly what it means. So there is a certain kind of surface given in the diagram by the graph of a certain function f, such that near every boundary point, the boundary of omega lies above the graph of that function. So in this sense, it's supported from the outside. So that's roughly what we mean. So returning to the main discussion, another result by Zimmer, 2017, states that in a bounded convex C strictly convex domain omega with C1 alpha smooth boundary, where alpha is in 0, 1, every complex geodesic of omega extends continuously to del D. So first of all, what do we mean by C strict convexity? In the C1 smooth case, which is the only case, if you take any boundary point and you consider the affine complex tangent space at that point, then that does not intersect the closure of the domain at any point other than that point. So in that sense, it's C strictly convex. That's what we mean by C strict convexity. As for C1 alpha smoothness of the boundary, that means that the domain has a defining function whose total derivative is not merely continuous, but also alpha Hölder continuous. So that is what we mean by C1 alpha smoothness. Neither of these results subsumes the other. This talk arises from a conjecture motivated by these two results. So first we make some observations on the stated results. First we introduce some notations. Bold J will denote multiplication by I in Cn, viewed as an R-linear map. So in particular, JV will be orthogonal to V relative to the usual real inner product on Cn, which we identify with R2n. D subscript V will denote the directional derivative in the direction of V for a unit vector V. And eta upper Xi will denote the unit inward normal to del omega at Xi, where omega is C1 smoothly bounded and Xi is in del omega. A careful reading of Zimmer's proof already shows that we can replace the condition del omega is C1 alpha smooth by there exists a defining function rho of del omega such that the particular directional derivative d j of eta Xi rho is alpha Hölder near every Xi in del omega. So this motivates the conjecture because we have already significantly reduced the smoothness assumption, regularity assumption. It suffices for a bounded convex domain in Cn to be C strictly convex and have just a C1 smooth boundary for all complex geodesics of omega to extend continuously to del D. This is a conjecture, but our result is a step towards this conjecture. So we turn to our results. So be a bounded convex C strictly convex domain with C1 smooth boundary. Assume that there exists a defining function rho and r greater than 0 and a non-decreasing function omega from 0 to r to 0 infinity satisfying a Dini condition such that for every Xi in del omega, that same directional derivative d j of eta Xi rho restricted to the n-dimensional ball bn Xi r has modulus of continuity dominated by omega. Then every complex geodesic of omega extends continuously to del D. So that is the result. So now we turn to main ideas behind the proof. So the main idea of Zimmer's proof and also of our proof is to adapt the proof of the fact that if we have an isometry between two Gromov hyperbolic distance spaces x and y, then it extends to a continuous map from x union x infinity to y union y infinity, where x infinity and y infinity are respectively the ideal boundaries of x and y. So it bounded convex domains in Cn to be Gromov hyperbolic with respect to the Kobayashi distance, because then we could at least hope to apply this method to prove an extension. However, bounded convex domains in Cn are not Gromov hyperbolic with respect to the Kobayashi distance in general. So we need a weaker result R that acts as a substitute for Gromov hyperbolicity. So this is that result. Let omega relatively compact in Cn be C1 smoothly bounded and C strictly convex. Let P nu and Q mu be sequences in omega converging to boundary points. Suppose limit as mu and nu tend to infinity, P nu Q mu O. So this is the Gromov product. You will see it defined below. Gromov product with respect to the Kobayashi distance is equal to infinity whenever P nu and Q mu converge to the same point, and that a weak form of the converse of this holds true. Then every complex geodesic of omega extends continuously to del D. R is implicit in Zimmer's work. So that's, I wanted to point that out. Now I need to say what a weak form of the converse of this means. So I will just tell you that. So just So this is what it means. So in one part, we demanded that if P nu and Q mu converge to the same boundary point, then the double limit of the Gromov product should be equal to infinity. In the other part, we suppose that P nu and Q mu converge to boundary points x and y, and we suppose that we know that lim sup nu and mu tend to infinity, P nu Q mu O is equal to infinity. Then while we may not be able to conclude that x is equal to y, we will be able to conclude that the complex affine tangent spaces at x and y are the same. So that is what we mean by a weak form of the converse. So that is what we mean. So returning once again to the main discussion. So we had dealt with this slide. This is done. So we are reduced to obtaining the conditions in R that shows that the hypothesis of R holds true for omega as in our theorem is the parametrization of inward pointing normals as K almost geodesics. These K almost geodesics are essentially geodesics up to a bounded error, namely log K, and their work is that they facilitate computation of the Gromov product, which is important because the Gromov product makes an appearance in R, result R. In turn, what allows us to parameterize inward pointing normals as K almost geodesics is the ability to embed copies of a model planar domain script D, whose Riemann map behaves well at 0 in del script D. Via the embeddings, Z goes to Xi plus Z eta Xi into omega in such a way that Xi plus script D eta Xi, the embedded domain, osculates del omega at Xi. This is an idea due to Zimmer. So I would just like to point out that the embedding in question is very natural. We are placing ourselves at the boundary point C and using the inward pointing normal to basically place our planar domain into the bigger domain. So the embedding Z goes to C plus Z eta C allow us, due to the distance decreasing property of holomorphic maps, to deduce K omega measurements from K script D measurements. In turn, the Riemann map condition allows us to write K script D near explicitly using rho D, the Poincare distance, with excellent estimates arbitrarily close to 0 in del script D. So this is where we need the invertibility of the derivative of the Riemann map at 0. So as I just said, parametrizing inward pointing normals as K almost geodesics only requires the Riemann map of our script D to have non-zero derivative at 0 in del script D. So searching in the one variable literature, we located the following result by Warshawski. If D is a relatively compact subset of C bounded by a Jordan curve gamma that has, in a neighborhood of some point P in gamma, a continuous tangent angle whose modulus of continuity satisfies a Dini condition, then the Riemann map of D has non-zero derivative at P. So the Dini condition in our theorem comes from the above. That is the Dini condition in Warshawski's result. So we end by defining a model planar domain that works. So script, so first I'll give the definition. I will provide an illustration a little later. Script D C tau is defined to be set of all z in C such that 0 is less than real part of z less than tau. Modulus of imaginary part of z is also less than tau, and real part of z is greater than C times h of imaginary part of z, where the function h is defined as follows. H of y is defined to be integral from 0 to y omega of t dt if y is greater or equal to 0, defined to be integral from y to 0 omega of minus t dt if y is less than 0. Please note that omega is the modulus of continuity that is given to us. It occurs in the statement of the theorem. So we are using that to cook up our domain script d theta. So I will give an illustration of what these domains look like.
So Anway, you have 4 minutes left.
Okay, yeah. So this is what they look like. So this is roughly what they look like. As you can see, they are constrained within a box of width tau and height 2 tau. And this curve is, I mean, the curve you can see ch of y. And clearly one can see that as one increases c and decreases tau, the domain script d c tau shrinks. So that is the point I will end on, that one can choose uh, C large enough and tau small enough so that affine images of script D C tau fit into omega. That will allow us to parameterize inward pointing normals as K almost geodesics. That in turn will allow us to obtain the conditions in R, and then we will get our result. So that concludes the talk. Thank you.
Okay, thank you, Anway. And the floor is open for some questions. Actually, we have 7 or 8 minutes left before. Yes, so if there is any question, please unmute yourself and ask the question.
So, Anwoy, a quick question. I'm sorry, I know that we have discussed the ideas behind this proof very often.
Yes.
But then, I mean, since ultimately the execution was yours, there's one thing I have forgotten.
Yes.
So you mentioned that you have these parameters capital C and tau.
Yes.
Which you adjust to be able to fit this this planar domain in that obvious C affine manner.
Yes.
At a boundary point.
Yes.
Now the boundary point is completely arbitrary.
Yeah.
What you're kind of saying is that one can choose. What is the order of quantifiers?
Yeah.
You can choose C and tau once and for all.
Yeah, once and for all, independently of all boundary points, such that it can be done at any C in del omega. Okay. That is the thing.
Yeah, go ahead. And you were saying?
I mean, the regularity that C1 Dini, in fact, the regularity C1 Dini, and because omega is fixed, it is given in the theorem. So that is also a kind of uniformity that allows us to find C and tau. That suffices.
I see. So the choice of the parameters doesn't depend on the oscillation point, because that omega has been stated as in the hypothesis as being independent of the boundary point.
Yes, yeah? Yes, it has been stated like that. Yes.
Okay. All right. Yeah. Thanks.
Yes. Anybody else? Comments or questions? Anything? So it seems we don't have any further questions. So thank you again, Anway.